Welcome to our session, Securing the IoT Supply Chain with DevSecOps. I'm Antonio Escalera, Senior Platform Engineer with Raft.
And I am Dan Morrison, a lead DevSecOps engineer, also here at Raft.
So today we're looking to provide an overview of some of the most impactful DevSecOps approaches and technologies available and explore how IoT manufacturers can strategically implement them to augment their security posture. We're not looking to provide a complete production-ready solution, but we will be covering a multitude of layers throughout the stack.
All right, and when we're getting started talking about securing supply chains, it's very important to make sure the entirety of your development process is performed with security at the forefront of your mind. You should be, from the first commit, implementing security in everything you do. And one quick way that you can do that is by signing those commits. It's relatively straightforward to generate a GPG key or PGP key if you've got them, and cryptographically sign all of your Git commits. This is going to make sure that nobody is creating commits in your repository impersonating somebody who should have the access to it. These commit signing can also be enforced at an organizational level within most modern Git source repositories. Now, going right in line with making sure that only trusted people can change code in your repositories is the idea of exercising the principle of least privilege when it comes to assigning permissions. It's all too common to come across open source software or public personal projects that are completely wide open in terms of allowing anybody with a valid Git account to create PRs, merge whatever they want into branches, and you're just opening the door wide open for attacks of this nature. So it's very important to configure those repositories, protect your branches, and make sure that only the right people with the correct credentials and authority within your organization are able to access certain source code repositories. When it comes to actually developing that application, it's additionally important to make sure those bits of software you pull in to your application are secure. So your third-party dependencies that you're using, it's important to have an agreed upon definition of secure within your organization so that you can understand what level of threat tolerance you're okay and comfortable with accepting. It's a dream of many to have 0 CVEs, but in reality, it's not always possible. So having a plan in place for remediating these types of findings is very important. And going hand in hand with a nice vetting process when you bring in dependencies is the idea that you should be scanning everything and keeping them up to date. So whether that's using something like Dependabot or Renovate to find new versions of dependencies that fix CVEs, or in general using things like Sneak and Trivy to scan to find CVEs within your application currently. Additionally, scans aren't always about vulnerabilities, and it's important to use those other types of scans as well. Even things as straightforward as linters, like a Golang CI or a Pylint, to find code smells, inefficient and insecure code within your project, can bring a lot of value. And if you want to go that extra mile and set up quality gates enforcing that quality standard, you can use something like SonarQube to do that. One last type of scan I will touch on is security scans. And for the purpose of finding hidden secrets in your repository. It's an easy mistake to make, and I'm sure it happens more than anyone would like to commit when you accidentally commit something like a TLS certificate into a Git repository. Tools like Trufflehog and Git leaks can be used to find unwanted commits of that nature to make sure that that doesn't make its way into an actual release. Speaking of building and releasing this secure software, the way that you design CICD for secure supply chains is different from anything we've done in the past in terms of software development. Long gone are the days where you can throw a rack in a closet, put Jenkins on it, and build your organization software artifacts. It's just not going to cut it anymore. The attackers today are more sophisticated and willing to go the extra mile. It's important to treat that build environment with the same level of care and security that you give to a production environment. And now one thing you can do within this build environment so that you know for sure that it is to be trusted is to generate a provenance document during your build process. So a provenance document is something that's going to have metadata with regards to this particular pipeline run that produced your software artifact. It's going to have things such as who was the Git committer that executed this pipeline, where was this pipeline executing, build ID numbers, commit SHAs, and the like to tie this unique document to your unique software artifact. With that provenance document and tools like Cosign and Sift, you could attest the provenance and later on in the deployment of your application, verify that images were produced where you thought they were being produced, the way you thought they were being produced, by whom you trust. Now, of course, it's important to have a secure build pipeline, but it's a little bit underwhelming if you aren't keeping everything secure. So one way you can do this is through GitOps. I think this is a great way to make sure that as soon as a new update is available, that you are getting it, you are installing it and remediating any potential vulnerabilities within your target environments. Now, you can use GitOps for applications, for the infrastructure supporting your workloads, even for the firmware itself. But one real consideration that you've got to take in mind is whether or not you're going to always have internet connectivity or whether you're going to have a sporadic connection. So this is something that's going to make a big difference in how you architect and design the automated updates of an IoT system, and especially when it comes to a sporadic connection. So it's important to make sure you've got some sort of process or microservice of sorts that is waiting, watching, checking for a connection to your update server. And the moment that you get that connection, begins to pull down any updated packages as needed for installation and updating offline. You want to make sure you're using what limited connection time you've got very wisely. So now that we've got an application that we're building securely and we've got a means of updating this thing, it's important to make sure that the hardware itself that you're running on is also secure. And to talk more about that, I will turn it over to AJ.
Thanks, Dan. So yeah, up next, talking about the network layer. So that includes YWAN, WLAN, and WPAN networks. This is important for actually getting the updates to the devices, as well as things like monitoring and remote control. You don't want your smart oven going to 500 degrees when you're not home, because some attacker was able to inject a malicious payload into the over-the-air update. So in order to facilitate this, it's important to integrate security throughout the layers of the networking stack. Technologies like 5G ACA and 802.1x provide access control, and EAP-TLS and IPsec provide encryption. And together they provide confidentiality and integrity in the software and controls that are submitted to the devices. and back to the host services. In addition, network segmentation and cloud application security brokers can be utilized to ensure that only traffic that you'd like is going to the specific services. Back to your host network or to the user equipment. Traffic monitoring with tools like NetFlow can help also ensure that traffic isn't being routed in weird ways or someone is injecting traffic into your networks. And finally, continuously evaluating your networks with tools like OpenVAS and OpenSCAP can be extremely helpful in ensuring the security of your network for your IoT devices. So now that we've got a way to connect to the devices, let's talk about remote attestation and field registration in the cases where devices are tied specifically to users' accounts. So one popular framework for enabling remote attestation is the TPM-enabled Remote Attestation Protocol, or TRAP. This protocol uses secure hardware located on the device that is tamper-resistant in order to facilitate secure communication and attestation of the software artifacts residing within the device. So it typically uses some sort of key that comes provisioned at manufacture time, as well as using dynamic values such as hashing the actual contents of the bootloader or using platform configuration registers to ensure that software artifacts are valid and signed by specific authorities. So now that the device is attested, one important aspect of actually performing that attestation is the secure boot process. Secure boot involves a root of trust inside of a tamper-resistant secure element, that TPM that we were talking about earlier, which establishes a chain of trust throughout the different components involved in actually booting the software. So the bootloader is verified by the TPM. The bootloader then verifies later stage firmware, such as those used for over-the-air updates, maybe a stage 2 bootloader. And then that stage 2 bootloader establishes trust with the operating system that's located on the device, as well as any applications that are on the device. The operating system verifies. So in order to facilitate the secure boot process, a critical aspect is the actual trusted execution environment. This is a separate, isolated environment that's specifically for secure code execution that has guarantees in the confidentiality and integrity of the code and data that is stored and executed within that world. It's achieved through hardware-based isolation. One popular trusted execution environment for IoT devices, especially ARM devices, is the trust zone. And this looks a little bit different for Cortex-A and Cortex-M processors. So your Cortex-A processors are kind of the more application processors. They're more of a full-fledged processor. So they have a memory management unit that's able to facilitate fine-grained control over specific memory regions. Whereas your Cortex-M is sort of a real-time application processor. And so it's more lightweight, and it uses a memory protection unit, which facilitates more coarse-grained access control over memory regions. This trusted execution environment is used heavily within the secure boot chain and the root of trust in establishing that remote attestation. And that's facilitated through the secure monitor and secure monitor calls. So now we talked a little bit about secure boot and trusted execution environments. we of course couldn't go without talking about the trusted platform modules. So these are hardware-based security devices that are used for secure storage, cryptographic processing, and are accessed through security functions stored within the firmware of the trusted platform module. These devices, like I mentioned, are tamper-resistant and evident, and they're typically integrated into the system board, usually on a separate chip. Some common tamper-resistant methods that they employ are ceramic shields or metal shields, also fine mesh wire across the actual silicon, such as within YubiKeys. And these different types of sensors can trigger either self-destruct or wiping of the actual trusted platform module. So that should the device fall into the wrong hands and somebody try and tamper with it, it's extremely obvious, and the device itself no longer enables connection to the network. So this is integral in establishing a root of trust. So you can be confident in the actual root of trust that is stored on the device. And it helps facilitate firmware and bootloader integrity verification. One of the critical components or aspects of the TPM is that it's able to facilitate system measurement or system configuration measurement. And it stores those measurements within the platform configuration registers. These registers are required to be set to specific values in order to unseal certain aspects that are required for the boot chain. So if any one of the platform configuration registers is not set to the appropriate value, then the system just fails to boot and it will not connect to the network. All this together helps to enforce device level security policies and monitor the overall security health of the device and facilitate secure over-the-air updates.
All right.
So now I'll pass it back off to Dan to cover the application layer.
Thanks so much, AJ. So one thing you can do within the application layer to secure your inter-service network communication is to implement mutual TLS and enforce that mutual TLS with a service mesh. So at the highest, most basic level, mutual TLS is just saying that when you've got a client and a server that want to securely communicate, that you should have a third party that is mutual to the two workloads that is able to verify both workloads should have access and know about one another's TLS certificates. So this is especially important within the IoT space due to the lack of complex authorization and login procedures. So it's going to be very unlikely that you're going to have a fully fleshed out and robust OIDC or OAuth2 authentication authorization protocol for your IoT device. So due to just being on the edge, having limited compute, a lot of times limited connectivity, some of those more robust authorization protocols just aren't available to you. MTLS is typically very lightweight. You can just set up a sidecar next to whatever workload you are running, and you can get all those benefits while helping to protect yourself from malicious attacks and bad actors that are in your environment. Now, that is great, but having mutual TLS is going to protect you once someone's already inside, once they're already in the environment, in your Kubernetes cluster. So it's important to make sure that they cannot get in, they cannot schedule their workloads at all. And one way you can do that is by using admission controllers. These are going to sit within the API request lifecycle of a Kubernetes cluster before your resource is ever scheduled. That is to say that that malicious workload could be prevented from ever beginning its boot process. How do we do this? So we do this using the cosign policy admission controller in conjunction with our secure build pipelines. Because we signed our images, because we attested our provenance document, and we attested our software bill of materials, we can verify these respective components at deployment time. We can protect entire namespaces from having any image scheduled that was not signed using a known key. We can ensure that no workload is able to be scheduled if its provenance document states that it was produced in any environment other than your organization's trusted build environment. And additionally, you can then use the attested software bill of materials and verify that this application that's trying to run does not have tons and tons of critical vulnerabilities to wreak havoc within your environment. Now, all of those things are great. However, what if you're not using assigned images? All too often, we're using open source, we're using Helm charts, things that we don't have full control over. In such a case, you can still use admission controllers to help keep your environment safe. You can use things like OPA Gatekeeper or Kyverno in order to analyze the resource manifests that someone is attempting to create within your cluster and secure your cluster from anything malicious. Now, an example of this might be protecting your kube system namespace or protecting a DNS-related namespace from anyone that might want to schedule something there. Get everything set up and lock it down using these admission controllers. So it's great to talk about all these things, but it's a lot more fun to see some of it in action. So I've got a quick little demo here just to show what it looks like when you're got one of these secure environments, you're deploying to it, and what it might look like if someone who shouldn't be deploying to it tries to. So first off, we're just going to show this deployment. This is our Helm chart using our trusted image. It was signed. It's been attested with an SBOM. It has no vulnerabilities. It should be allowed to run. But if we tried to schedule something into a namespace that's protected, in this instance, the kube system namespace, Gatekeeper is going to prevent that resource from being created because nothing should be allowed to be created in that namespace. And now, even if an attacker got in and somehow got your cosign key, they were able to sign an image with the trusted key. Their workload is still going to be prevented by our cosign policy that is checking for CVEs. In this case, we have a policy in place to verify the absence of the log4shell vulnerability that has wreaked havoc over the past some odd year. So with that, I'd love to open it up for questions if we have any time or anything in the chat.
Five minutes. I appreciate you showing us that example. I think that kind of brought everything together at the end. You know, the actual implementation of such things and what they look like in a Kubernetes cluster. Yeah, I think I appreciate you also mentioning some of the tools that we could use to get started. I've seen in some of the programs I worked with where there may be a gap in after you get a tool and how you actually configure it. And I think that leads to kind of like a general question I have that, you know, at the beginning of your presentation, you discussed a setting agreed upon standards for how you handle remediation, vulnerabilities, what kind of packages you're using and how they're approved and that sort of thing. I think that's an important discussion that needs to happen in every organization. Can you give our viewers kind of any advice on how to facilitate that sort of thing?
Yeah, absolutely. So I think one good way to sort of approach it, because it's a tricky problem, it's a rather big problem to solve, is to try and go from the out in, try to capture as much as you can first. Are you comfortable with say blacklisting an entire registry, right? Maybe you want to say, hey, when it comes to Docker images coming in, got to be on Docker Hub, nothing else. Or if you're working in the DoD space, you might say, hey, it has to be an Iron Bank for our purposes, and I'm not trusting anywhere else as a base image. If you can make some of those sweeping decisions, if that's something that's possible, I think that's one way to get a real quick leg up on it. Now, you did mention tooling, and I neglected to put this on that slide, but there is a little bit of newer tooling that's come out that can be really useful, even for this, for assessing whether something is to be trusted. That's OpenSSF scorecards. So there's this very cool little technology. You can kind of analyze something and get quantified results about how secure is it, what sort of risk are you taking on by bringing this dependency or this piece of infrastructure into your setup. So I think that's what I would have to say. Kind of try to go from out in first. Don't try to solve all the problems all at once. See if you can make some big sweeping changes, some sweeping chunks to just in general improve that posture. Then get a little more fine-grained with it, right?
Yeah, thanks. That's excellent. Thanks for that answer. I like that. I think it's kind of like, you have a bucket, right? Or an upside down inverted pyramid that you want to kind of narrow down to.
Yes, right.
Kind of take the first group off the board and that sort of thing. And yeah, in our space, Iron Bank is a big component of it. Yeah. So now we get into some of the other things. AJ, I know you specifically discussed a lot of from the IoT side of things, network layer. I appreciate you going through all that. I was just curious, is there any particular advice? I mean, you talked about actually like appliances and that sort of thing. What about testing in the development environment? How would you handle that with things like, hardware in the loop, that sort of stuff? Is that all part of this?
Yeah, absolutely, and that was exactly what I was going to mention. Using hardware in the loop, having the actual hardware within a rack somewhere that you're able to access and push changes to is critical in ensuring that not only the security of the device, but also ensuring that breaking changes aren't applied, especially in the instance where the network isn't always connected. So some devices may have higher versions than others of the actual software or firmware that you're deploying onto them. And so it's important to make sure that skipping an update or two doesn't actually cause problems with the actual deployment or communication with those devices.
Okay, great. Yeah. I guess that goes back to the remediation that we discussed, right? It's like have a plan in place to update such things as needed and that sort of thing. So yeah. So I think we're coming up on time here. I just want to thank you again, AJ Escalera and Dan Morrison from Raft. Thanks for that great presentation.